Welcome back to my video series on machine learning in Scikit-learn. In the previous video, we learned how to properly evaluate a model using the train-test-split procedure. We were focusing on classification models, and our evaluation metric was classification accuracy. In this video, I'll be covering the following. How do I use the Pandas library to read data into Python? How do I use the seaborn library to visualize data? What is linear regression and how does it work? How do I train and interpret a linear regression model in Scikit-learn? What are some evaluation metrics for regression problems? And how do I choose which features to include in my model? So far in this series, we've focused on classification, in which the goal is to predict a categorical response. In contrast, regression is a type of supervised learning in which the goal is to predict a continuous response. Regression problems are the focus of today's video. Before we start talking about regression, we're going to choose a data set and read it into Python using Pandas, an extremely popular library for data exploration, manipulation, and analysis. If you're using the Anaconda distribution of Python, Pandas and its dependencies are already installed. Otherwise, I've linked to the installation instructions. We'll start by importing Pandas in the conventional way, which is to import Pandas as PD. I've selected a dataset for today's lesson from the book An Introduction to Statistical Learning. The dataset is posted online as a CSV file, which stands for comma-separated values. CSV files are a very common way to store data in which each observation is a single line in the file, and the fields are separated by commas. Pandas has a function for reading in CSV files called readCSV, and you simply pass in the name of the file. You can read files from your local computer, or you can actually read files directly from a URL, which is what I'm doing here. I'm going to save the results as an object called data, and then run the head method on that object to see the first 5 rows of data. The results are displayed kind of like a spreadsheet. This object is called a Pandas data frame, which consists of rows and columns. A single column in a data frame is known as a Pandas series. Anyway, Pandas has figured out that the first row in the CSV file contains the column headers, namely TV, radio, and so on. However, it looks like there's an unnamed column that contains sequential numbers starting at 1. So those are probably just the ID numbers for those observations. I'm going to take those numbers and use them as the index, which is how Pandas identifies the rows. The default index is sequential numbers starting at 0, shown on the left side in bold. To figure out how to set those ID numbers as the index, let's look at the help for readCSV. I'll click within the parentheses and then hit Shift-Tab on my keyboard twice. You can see that readCSV has a ton of parameters that allow you to control the CSV reading process in great detail. In our case, we need to use the index call parameter, which allows us to set a specific column as the index. So we'll type index col equals 0, and then rerun this cell. You can see that the unnamed column has now been set as the index. Data frames also have a tail method, which shows you the last 5 rows. Because the highest index number is 200, we would assume that the data frame has 200 rows, but we can confirm this by printing out its shape attribute. The output tells us that there are 200 rows by 4 columns. Now that we've read in the data, let's talk about the data and how to structure it as a supervised learning task. The first column, TV, shows the amount of money in thousands of dollars spent on TV ads to advertise a single product in a given market or city. So for example, in market 200, about $232,000 was spent on TV ads. Similarly, $8,600 was spent in market 200 on radio ads, and $8,700 was spent in market 200 on newspaper ads. The sales column represents the sales of the product being advertised in that market in thousands of items. So in market 200, a quantity of 13,400 was sold. In this case, let's attempt to predict sales based on advertising dollars. Thus, we'll use TV, radio, and newspaper as the features, and we'll use sales as the response. Because our response variable is continuous, this is a regression problem. And just to be clear, our dataset has 200 observations, and each observation represents a single market. Before we start working through the machine learning process, let's visualize our data to get a better feel for it. I'm going to use the seaborn library, a Python library for statistical data visualization that is built on top of matplotlib. If you're using Anaconda, you can run conda install seaborn from the command line to easily install it. For other Python users, I've linked to the installation instructions. Let's go ahead and import seaborn as SNS and also run matplotlib inline, known as a magic command, to allow plots to appear within the notebook. Often, the first relationship you want to visualize is the relationship between each of the features and the response variable. This can easily be done using seaborn's pair plot function, which produces pairs of scatter plots for each x and y variable that you specify. These plots are a bit small, and so I'm going to change the size and aspect ratio so that I can see the data more easily. You can see that there is somewhat of a linear relationship between TV and sales, meaning that as TV advertising increases, sales increases in a somewhat linear fashion. There appears to be a less strong relationship between radio advertising and sales, and a weak relationship between newspaper advertising and sales. We can actually ask seaborn to plot these relationships by adding one more argument to pair plot. Seaborn has added a line of best fit as well as a 95% confidence band. Because there appears to be a linear relationship between the features and the response, this is a great candidate for the linear regression method. Linear regression is quite a deep topic, but I'm just going to give you a brief introduction before we implement it in Scikit-learn. To start, I want to make clear the difference between regression and linear regression. Regression, as it relates to machine learning, is simply a type of supervised learning problem in which the response is continuous. Linear regression is a particular machine learning model that can be used for regression problems, and it just happens to have the word regression in its name. Anyway, linear regression is a very popular modeling technique for four main reasons. First, it runs quickly, which becomes increasingly important as the size of your dataset increases. Second, there's no tuning required in the way that we had to tune the value of k for k and n, which makes it easy to get started. Third, it's highly interpretable, meaning that you can easily understand the model and how it's making predictions. And finally, it has been studied for many years and is well understood, and thus there's a vast amount of literature on the topic of how to use linear regression properly. In terms of drawbacks, the main drawback to linear regression is that it's unlikely to produce the best predictive accuracy as compared to other models. This is because linear regression presumes a linear relationship between the features and the response. If the relationship is highly nonlinear, as happens in many real-world scenarios, linear regression will be unable to effectively model the relationship, and thus its predictions will not be very accurate. Let's take a look at the functional form of linear regression in order to gain an understanding of how it works. It can be represented as follows. Y equals beta naught plus beta 1 x1 plus beta 2 x2 all the way to beta n xn, in which n is the number of features. Let's briefly discuss each of the model terms. Y is simply the response value. Each of the features is represented by an x variable, and each feature has a coefficient. In this case, we have three features, TV, radio, and newspaper, and each feature has a beta value, beta 1 and beta 2 and beta 3. Finally, beta naught or beta 0 is called the intercept, which is the value of y when all of the x values are 0. These beta values, as well as the intercept, are learned during the model fitting process using what is called the least squares criterion. Basically, linear regression seeks to find the line that best fits the observed data, as we can see here. It defines the best line as the one that minimizes the sum of squared errors, which is really just the sum of the squared vertical distances between each point and the line. Once this line of best fit has been learned, it can be used to make predictions for sales given any set of feature values. Before we start the modeling process with Scikit-learn, we first have to define the feature matrix X and the response vector Y. Remember that scikit-learn is expecting X and Y to be NumPy arrays. However, we're lucky in that Pandas is built on top of NumPy, meaning that there is a NumPy array actually storing the data frame data. Therefore, our X can be a Pandas data frame, and our Y can be a Pandas series, and scikit-learn will understand how to access the underlying NumPy arrays. Let's start with X. What we need to create is a data frame that contains only our 3 feature columns. So first, let's create a Python list called feature calls that contains the names of our feature columns stored as strings. Then we can say data, open bracket, feature calls, close bracket, which tells Pandas to select a subset of the original data frame columns. You will often see these 2 steps done in a single line, as shown here. These double brackets can be confusing, so just remember that the outer bracket is how you tell Pandas that you want to select a subset of data frame columns, and the inner bracket is how you define a Python list. Finally, let's run the head method on X to confirm that the operation worked. You can see that it's still a data frame, but now containing only our 3 feature columns. We can use Python's type function to confirm that it's a data frame, and we can print the shape attribute to confirm that it contains 200 rows and 3 columns. Now let's move on to Y. Our response value is sales, and we can select the sales series from the data frame using the bracket notation. This time, however, you only use one set of brackets, and you pass in a string containing the name of the column. Alternatively, if there are no spaces in the name of the column, you can select the sales series as an attribute of the data frame. We'll again run the head method on the series to check the results. And again, we can use the type function to confirm that it's a series, and print the shape attribute to confirm that it's a one-dimensional array with length 200. Our final step before using linear regression is to split X and Y into training and testing sets for proper model evaluation. As we saw in the last video, we use the traintestsplit function to split X and Y into 2 objects each. We'll also print the shapes of these objects. We didn't specify the size of the testing set, and so it defaults to using 25% of the data for testing. Finally, let's actually build our linear regression model using scikit-learn. We follow the same pattern we've used previously, which is to import the model, instantiate the model, and then fit the model to the training data. Every model differs in terms of what occurs during the fitting step. In the case of K-neighbor's classifier, all the model did during fitting was to memorize the training data so that it could later calculate the distance between a new observation and the existing observations. In the case of linear regression, the model is learning the intercept and coefficients for the line of best fit. Then it has an easy formula for making predictions during the predict step, which we'll see below. As I mentioned previously, linear regression is a highly interpretable model. Let's see what that means by printing out the intercept and the coefficients and then interpreting them. The intercept and coefficients are stored in separate attributes of the linreg object, which is why I use the dot notation to access them. You'll notice they both have a trailing underscore in their names, which is Scikit-learn's convention for any attributes that were estimated from the data. Anyway, the coefficients are stored in the coef attribute in the same order as they were stored in the feature matrix X. It can be hard to remember that order, so I like to use Python's zip function to pair each of the feature names from the feature calls list with the coefficients. I've plugged the intercept and coefficients into the linear regression formula. This formula now allows us to input the TV, radio, and newspaper ad spending in a given market and output a prediction for the amount of sales, which is the Y variable. Let's now interpret the TV coefficient, which is 0.0466. It means that for a given amount of radio and newspaper ad spending, a unit increase in TV ad spending is associated with a 0.0466 unit increase in sales. That makes sense when looking at the formula because increasing TV by 1 would mathematically increase the Y response variable by 0.0466. However, keep in mind that a unit of ad spending represents $1,000 and a unit of sales represents 1,000 items. Thus, the more clear interpretation of the TV coefficient is that an additional $1,000 spent on TV ads is associated with an increase in sales of 46.6 items. This same process could be repeated to interpret the radio and newspaper coefficients. Again, this level of interpretability is why linear regression is such a popular model for regression problems. Before we move on to the prediction step, I want to add two important notes. First, I was careful to use the phrase associated with when interpreting the TV coefficient because this is not a claim of causation. It's a very difficult problem to determine causation because that relies upon having access to every possible factor that could have influenced sales, whereas all we have is data on ad spending. This is why machine learning tends to focus on association rather than causation. Second, I want to make clear that linear regression coefficients can be negative. For instance, if an increase in TV ad spending was associated with a decrease in sales, the beta 1 coefficient would have been negative. Anyway, let's use our fitted model to make predictions on the testing set, which we store in ypred. Previously, we've used classification accuracy as our evaluation metric, though that metric is not relevant for regression problems because regression problems have a continuous response. Let's take a look at some common evaluation metrics for regression, and then choose one to evaluate our predictions. We'll start by creating some example numeric predictions, and then evaluate them using a given metric so that we can get a feel for how those metrics work. In this contrived example, the true response values are 100, 50, 30, and 20, and the predicted values are 90, 50, 50, and 30. Mean absolute error, or MAE, is the simplest metric. It's the mean of the absolute value of the errors. The error is simply the difference between the true and predicted values. So if we wanted to calculate our MAE by hand, we would add 10 plus 0 plus 20 plus 10, and then divide by 4. Scikit-learn can also calculate the mean absolute error for us using a function from the metrics module. The MAE in this case is 10, which you can just think of as the average error. Mean squared error, or MSE, is very similar to mean absolute error, except that each of the errors is squared. So we would calculate 10 squared plus 0 squared plus 20 squared plus 10 squared and divide the total by 4, which would be 150. Mean squared error is a bit harder to interpret than mean absolute error. Root mean squared error, or RMSE, is identical to mean squared error, except that the square root is taken at the very end of the calculation. I use the square root function inside of the NumPy package to calculate the square root, though there are other ways to do this. Our RMSE is around 12. You might have noticed that our RMSE is a bit larger than our mean absolute error due to the fact that RMSE squares the errors and thus increases the weight of larger errors. Let's briefly compare these metrics. Mean absolute error is certainly the easiest to understand. Mean squared error is more popular than mean absolute error since it punishes larger errors, and it tends to be the case in real-world applications that minimizing larger errors is more important than minimizing smaller errors. But root mean squared error is even more popular than mean squared error because RMSE is interpretable in the Y units. In other words, our MSE of 150 is a bit hard to interpret, while our RMSE of around 12 is easier to put into context since it's in the same units as our response variable. As such, let's go ahead and choose RMSE as our evaluation metric and then evaluate our sales predictions. We'll now compute our RMSE and see that it's about 1.4. This seems pretty good, given that our sales ranged from about 5 to 25. So, what should we do from here? In the last video, we saw that traintestsplit could help us to choose between different models and different tuning parameters. Linear regression doesn't have any tuning parameters, and we haven't yet learned other models for regression, so those options don't apply. However, note that traintestsplit can also help us to choose between features. When we visualize the data, we saw that the newspaper feature appeared to have a very weak correlation with sales. Thus, let's try removing that from our model and see how that affects the RMSE. This looks like a lot of code, but it's really just a repeat of the code we've used previously, except that newspaper has been removed from the list of feature calls in the first step. Thus, our feature matrix X only contains TV and radio. We again do a train test split, fit the model, make predictions, and compute the RMSE. The RMSE this time is about 1.39, a slight decrease from our previous model. Unlike classification accuracy, in which higher numbers are better, error is something we want to minimize, and thus lower numbers for RMSE are better. Thus, our new model that excludes newspaper is performing slightly better than when it was included, indicating that the newspaper feature should be left out of the model. You could repeat this process with different combinations of features, and then select the combination with the lowest RMSE as the best combination to use for this particular problem. I've listed some great resources here for going deeper into linear regression, Pandas, and seaborn. First is a longer notebook on linear regression that I use when teaching my data science class. It uses the same data as this notebook, but it also includes other topics such as confidence intervals, hypothesis testing, p-values, and R-squared. It also demonstrates linear regression using stats models, which is a Python library focused on statistics. Next is Chapter 3 from an Introduction to Statistical Learning, which also uses the same data as this notebook, but goes into linear regression in much more depth than either of my notebooks. After that is a quick reference guide to applying and interpreting linear regression, which I wrote to summarize many of the key points from Chapter 3. Finally is an excellent introduction to linear regression by Robert Now of Duke. It's very detailed, mathematically thorough, and includes lots of useful advice if you want to make the most of your linear regression models. For an introduction to Pandas, I really like this 3-part tutorial written by Greg Rita. If you're trying to read your own CSV files into Pandas, I recommend that you read through the Read CSV documentation. And if you're trying to read a different type of tabular file into Pandas that is not comma delimited, you'll want to check out the Read Table documentation. If you'd like to learn seaborn, the official tutorial is quite good, and the example gallery will give you a quick look at most of its functionality. Congratulations on getting this far in the series. I've got a lot more content planned, and your comments have been helpful in shaping the series, so thank you. One question I have for you this week is whether you'd like me to focus more on Pandas, or instead focus exclusively on Scikit-learn. Let me know in the comments section below, and then I'll see you again soon.